its conjugate base is propanoic acid. Okay? We're going to work another kind of problem. The next couple slides, this one, and I think the next one, maybe the next two. Yeah, these next 3 slides. This is what I call a buffer problem. You will have a problem like this on the exam. I'm going to write that. You will have a problem like this on exam. So pay attention. This is a 3-step problem. Okay, this would be part 1 of the problem. This would be part 2 of the problem, and this is going to be part 3 of the problem. It's a 3-part problem. It's a really big, long problem. And you do use the Henderson-Hasselbalch equation, okay? So, again, pay attention, take notes, work this out with me so that you know how to do it on the exam. All right. Part 1 says, what is the pH of a buffer solution made if we have 0.1 molar HF? This is our weak acid. How do I know? We have a hydrogen here. And 0.12 molar NaF. Okay, anytime you throw a cation on it, here sodium is a spectator. Okay, so the real thing you need to recognize is that this is F minus. This is our conjugate base. Okay. Sometimes they'll put a cation with our conjugate base, because usually most conjugate bases carry a negative charge. All right, so we have 0.1 molar of our weak acid, we have 0.12 molar of our conjugate base, and we're given the Ka of our weak acid. And so we want to know, what is pH? Well, you just plug everything in. First, though, we need to get pK. We're going to use the Henderson-Hasselbalch equation. We need to get pK, and then we're going to plug in these concentrations and solve for pH. So pK equals the negative log of 3.5 times 10 to the minus 4. What do you get when you do this? I actually need to solve for that. So plug this into your calculator. Negative log of, what is it? 3.5 times 10 to the minus 4. And I got that pK equals 3.46 if you round. Okay. Now we just plug all of this in to the Henderson-Hasselbalch equation. pH equals 3.46 plus the log. So in the Henderson-Hasselbalch equation, it's plus the log, not minus the log. And we're going to put what goes on top. The concentration of the conjugate base goes on top. And that is right here, NaF. So 0.12 molar divided by the concentration of the weak acid, 0.1 molar. All right, so we're going to do the negative log. Sorry, not negative, just the log of 0.12 divided by 0.1. And I got 0.079. So we'll do 3.46 plus 0.079, and you should get that the pH is 3.5, if you round, 3.54. That equals the pH of a buffer solution that has these concentrations of weak acid and conjugate base. Okay, so part 1 of a buffer problem is calculating the pH of your buffer solution. All right, so we did that. Now let's go to part 2. What's going to happen? It says, what is the pH of 1 liter of the same buffer system? We have 0.1 molar HF, 0.12 molar NaF. This is our weak acid. This is our conjugate base. And it says, what's the new pH when you add 0.02 moles of NaOH? So you can see what we're doing here is we're adding a base. And remember, bases can potentially raise the pH. So how will the buffer respond? I'm going to draw out our buffer diagram really quick. Remember, anytime you have base that you're adding, it is going to react with the weak acid. This weak acid is going to donate its H plus right here, and they are going to make water, and then what's left over? A minus. So we're going to use up some of the weak acid, and we're going to make more conjugate base. So when you add base to a buffer system, the concentration of your weak acid is going to go down. The concentration of your conjugate base will go up. I'm gonna write that out so you guys know that. When base is added to a buffer, here's what happens. The concentration of the weak acid, HA, goes down, and we're going to create more of the conjugate base because of our diagram over here. All right, so you definitely need to know this. Now, by how much is it going to go up and how much is it going to go down? Because to use our Henderson-Hasselbalch equation to solve for pH, which is what the question's asking for, we need to know what are our new, if these are going to change once they react with all the base we add, we need to find new concentrations of A minus and HA. Okay, we know that HA is going to go down. We know that A minus is going to go up, but what we need to know is by how much, so that we can plug these new concentrations into our Henderson-Hasselbalch equation. We already know the pKa. Okay, that doesn't change. Same buffer solution, so we'll just plug pKa in when it's time. But we need to resolve for concentration of A minus, concentration of HA, plug those in, and get a new pH. So the way we do this, you might have heard of this before. We create what's called an ICE chart. Okay, I stands for the initial amounts of HA and A minus. C stands for how the concentrations change, how they change. And then E stands for the new equilibrium concentrations of HA and A minus. And it is E, these new concentrations are what you plug in to your Henderson-Hasselbalch equation, okay, to solve for pH. There we go. So let's create an ICE chart. All right. So our initial concentrations of HA, I'm just going to make a column for HA right here. And I'm going to make a column for A minus. The problem gives us our initial concentrations. We have 0.1 molar of HF, which is, that might look confusing. We can be more specific. There we go. And we can go ahead and call the conjugate base. I'm just going to relabel it what it is for this problem. It is F minus. Okay? Or if you write sodium fluoride, that's fine too. But our initial concentration is 0.12, and this is units of molarity. How are they going to change? Well, they're going to change based on the amount of base that we add. Notice we're in concentrations of molarity. That's what the M's stand for right here. So we need to figure out how much base do we add in molarity. Well, we're given moles and liters. How do you solve for molarity? We'll do that right here. Remember, molarity equals moles over liters of solution. So to get the molarity of NaOH, I'm going to do 0.02, that's a 2, moles divided by 1 liter. Okay, and my molarity should be 0.02 molar. Okay, this is the molarity of what? Of NaOH. And that's what I'm going to plug into column C right here. So remember we said the concentration of HA, which is our weak acid, is going to go down. Well, it's going to go down by how much? 0.02. So I'm going to put a minus sign in the HF column. It's going to decrease the amount of HF by 0.02 molar. And we said the concentration of A minus is going to go up. So I'm going to put a plus sign in my ice chart in my column for my conjugate base. And it's going to increase by 0.02 molar. Okay, this is essential. Whenever you add base to your buffer, it's always going to decrease the column of the weak acid, and you're going to add to the column of your conjugate base. Okay, now we're just going to solve for E. So we have 0.1 minus 0.02. So what we should get is 0.08 molar. That's our new concentration of what? Of HF. And then add up the other column for the conjugate base. 0.12 plus 0.02 should give us 0.14 molar. So we have now solved for our new concentrations. And remember, down here we said after we get our new equilibrium concentrations, that is what we plug in to the Henderson-Hasselbalch equation to solve for pH. So I don't have a lot of room left over, and so I'm going to erase this down here so I can keep working. So let's do that. Henderson-Hasselbalch says pH equals pKa. What was pKa? We solved for it up here. It did not change because we have the same buffers, so 3.46 plugged in pK plus the log. What goes on top, what goes on bottom? The conjugate base always goes on top. So remember that F minus, this is our concentration of conjugate base. So the new concentration is 0.14 molar divided by, we do the weak acid, goes on bottom, so 0.08 molar. Now we have a complete Henderson-Hasselbalch equation. So we're just going to plug all that into your calculator. So you're going to do the log of 0.14 divided by 0.08, and you should get 0.24. So you'll do 3.46 plus 0.24, and your pH is now 3.70, right? Yep. That's our new pH. So you can see we started out with a pH of, what did we solve for in part 1? Our pH we solved for initially was 3.54. And when we add NaOH, how good did the buffer do? Well, it only changed pH by a little bit to 3.70. So not too bad. The pH went up by just a little bit, but it did a pretty good job of maintaining pH at or around its original pH. So you can see these buffer problems are really long because that is only step 2.